All right, hey everyone, I'm back again with another MCAT question of the day. Thanks for tuning in. Today's question is going to be about friction. And so, even if you're not taking the MCAT, it's just a great way to learn about friction. So, I hope you stick around. So, with that being said, let's go straight into the question. And the question says, on a rainy day, what happens to the coefficient of friction between a car's tire and the road? And right below, right here, I have this handy dandy diagram to show you what I'm saying. So, let's pretend that the car is moving from left to right. We're going left to right, and that would mean that the car's tires are rotating clockwise, right? What I want to know is relative to a sunny day, what's happening between the friction here? This moment of contact between the car's tire and the road, there's friction, right? Friction I'm going to talk about in a bit. I'm going to define it, but I want to know what happens to that friction when there's water involved. Does that friction increase? Does it decrease? Does it stay the same? Or can you not determine what exactly happens to it? Um, and again, I didn't make this clear already, so I want to make sure I make it clear. I want to know what happens to the coefficient of friction relative um, to a sunny day. Okay, so on a rainy day, the coefficient of friction might decrease compared to a sunny day. Does it increase compared to a sunny day? Does it stay the same, or can you not determine it? Before we can get into any of this, let's talk about what friction actually is. Friction is basically a force arising from two surfaces, right? Two surfaces, in this case the tire and the track, or the tire and the road, that rub against each other. So force arising from two surfaces rubbing against one another. Okay, so let me give you a perfect example of this right now. So you guys are all watching the video. If you just take your two hands and rub them right next to each other and rub them super fast, and you can't see what I'm doing, but if you rub them super fast, you'll see that they start to heat up. And that's because the two surfaces, in this case, your two hand palms, as they rub against each other, there's heat being generated there. That's friction. If you wanted to quantify friction, which not a lot of people want to do, but it's a good thing to try to know. The quantification of friction is given by this handy dandy formula. The frictional force is equal to the normal force, which I'm going to go over. The normal force times this thing, which is called mu, and mu is known as the coefficient of friction. So coefficient of friction. So, first of all, let me talk about both of these. What is the normal force? The normal force is basically equal to the force that kind of props an object up. So you can think about a table, right? And let me put a box on a table. Um, the box obviously has a weight, right? The weight of the box is going to pull it down because it's being pulled down to gravity. The normal force, though, the normal force is the thing that's keeping the box up. This is the normal force. And, you know, if the weight was the only thing acting on the box would accelerate downward, right? But it doesn't actually do that because the normal force on the from the table to the box keeps it up. So the normal force is kind of like the force keeping an object up, right? Force keeping object up. See, and then the coefficient of friction is basically a number that's greater than 0. It tends to be less than 1, but I can't say it's always less than 1. There are times when the coefficient of friction is greater than 1, but it tends to be greater than 0 for sure, and usually around at most 1, sometimes a bit higher. So let me give you a big example of this. So let me give you some examples now, okay? I'm going to give you one example here of concrete and rubber and ice and ice. And for now, I'm going to refer, obviously, to a coefficient of friction. And for the physicists in the audience, I'm going to be referring to the coefficient of static friction. But for anyone who doesn't really know the difference between static and kinetic friction, you don't need to know it. I'm just going to try to make a point. So in our first example, I want to have concrete and rubber. So let's just say this is concrete, and then this will be a rubber tire, right? Right here. The coefficient of friction is referring to the interaction between these two interfaces. On this one, I'm going to refer to ice and ice, right? If you repeat two pieces of ice together, the coefficient of friction I'm referring to is the interaction between them. And so, what exactly is going on here? Well, the coefficient of friction between concrete and rubber is 1.0. All right, and that's actually relatively high because, as I mentioned to you before, coefficient of frictions tend to be between 0 and 1, and so 1 is already pretty high. But to put this into context, between ice and ice, the coefficient of friction is around 0.2. Okay, that's really low, and this makes perfect sense because if you've ever rubbed rubber against concrete, you'll realize that there's a lot more friction there. Like, you actually know it's much harder to rub rubber against concrete than it is for ice and ice. Ice and ice is much more smooth, right? When you rub ice and ice together, they flow right across each other with relative ease. But when you have rubber against concrete, it's really hard to move. This is harder um, to move. On the other hand, moving ice on ice is easier to move. So with that being said, what's going on with our tire? Under normal conditions, at this interface right here, what you actually have going on is that the tire will exert a force on the road, right? The tire pushes on the road this way. The tire on road. Right? So this is a force not on the tire. It's a force that the tire exerts on the road to the left, because if the tire is moving clockwise, right, then it's going to exert a force on the road that's to the left. But because of Newton's third law, the road will exert an equal and opposite force in the forward direction. And believe it or not, this is the force of friction. So friction is actually something that's keeping the car moving forward, okay? And obviously, because the tire is steady on the ground, there's a normal force on the tire that the road is exerting because the tire has its own mass that's going down, mg, right? So the normal force in this one is equal to mg. But the point is, the frictional force in this case is equal to our coefficient of friction times the normal force, right? And in this case, the frictional force is going to be equal and opposite to the force that the tire exerts on the road. Remember this force right here, I have to highlight this because I can't tell you how many times students get it confused. This force at the bottom I'm drawing right here, this force is the force of the tire on the road. It's not an actual force on the tire. But this force is a force on the tire, but it's an equal and opposite force because of the result of Newton's third law with this force initially on the ground. Okay? Cool. All right, now we can actually move forward. So how does rain change this? How does rain change this? So you'll see my handy dandy drawing here, and you'll see that I've drawn rain right here with a thin layer of blue highlighter. So when you have rain, now you kind of have rubber, right? You have this rubber tire. Now you have rain, and then at the bottom, this bottom part right here is the concrete, right? So now you don't exactly have rubber and concrete. Now you have rubber, rain, and concrete. And if you go back, remember look at the left of the screen right now. If you recall, the coefficient of friction between rubber and concrete was 1, and between ice and ice was about 0.02. Okay, so it's hypothetically easier to assume that if you have rubber and then you have concrete and then you have a little bit of rain, that the resulting coefficient of friction is going to be the resulting coefficient of friction is going to be less than 1, but greater than 0.02, right? Because 1 is for pure rubber and concrete. Pure rubber and concrete. And 0.02 is almost for like water on water, because ice is just frozen water. Ice on ice. And we know that when we add water to the road, it's much harder for us to have that frictional force than it was in the past. So what theoretically is happening is that the coefficient of friction is actually going to decrease. So when rain is present, this frictional force that was initially present is actually going to be less, because the coefficient of friction is going to decrease. Because remember, pure rubber and concrete was 1. And when we have rain, there's no more pure rubber and concrete. The rubber of the tire is now hitting water in a sense, and then it's hitting the concrete. And so if we actually go back to the original question, the coefficient of friction between a car's tires decrease. And this is something that you'll probably have to drive in the rain. You drive a lot more slowly. Friction makes it harder to accelerate, right? it makes it much harder to accelerate because you're not getting enough traction between the ground and the tire because there's this nice thin layer of rain that usually makes friction much harder to work for you. And so with that, the answer is B. Really hope you guys enjoyed the video. This is a great conceptual question. Again, something that is easily found in the MCAT, but also just a great way to understand friction. Students often think of friction as something that slows you down. But in this case, friction is actually something that you use to move forward. And even when you walk, friction is responsible for moving you forward because you push down on the ground, and the ground, in an equal and opposite way because of Newton's third law, pushes you forward, much like how the car's tires push a car forward. And with that, I hope you guys enjoyed the video. Give it a big thumbs up if you did, and see you in the next one.